Today, the topic I'd like to talk about is a machine learning approach for describing water OH stretch vibration. This talk is provided by the Center for Molecular Spectroscopy and Dynamics, Institute of Basic Science in South Korea. Water is essential in our life, and we cannot live without water. Water is a simple molecule consisting of an oxygen and two hydrogen atoms. Water is one of the essential molecules for life on this planet. Water is ubiquitously found in numerous processes in chemistry and biology. For a physical chemistry point of view, water has some peculiar properties, such as its density is maximized at 4 degrees Celsius. Many scientists have been doing research to understand the various aspects of water in gas, liquid, or liquid and solid states, or other various reaction systems. Among the many experimental tools, infrared spectroscopy is one of the major experimental devices to probe the structure and dynamics of water molecules in various situations. Infrared or IR spectroscopy uses lasers at infrared frequency range to investigate molecular processes. When infrared laser light is given to a sample, the sample gives a spectrum after interaction with the incident laser light. This spectrum is a result of the interaction with the light and the molecules in the sample. This spectrum contains information about the structural and dynamical information about the molecular system. To interpret these vibrational spectra, we need a theoretical or computational tool to calculate the vibrational spectra from a given molecular structure. If we have such a tool based on molecular level pictures, it can be a great help in analyzing experimental spectra, even when the feature of the experimental spectra is very complicated. A single water molecule has three normal modes: bending, symmetric OH stretch, and asymmetric OH stretch. These vibrational mode gives a single peak for an isolated water molecule. But when the water molecule is surrounded by other molecules in liquid or solid phase, the interaction with the surrounding molecules makes the vibrational peak shifted, and the width of the peak is also changed. The amount of change of the peak position and width contains information about the interaction of a water molecule with the surrounding other molecules. The focus of the present work is to predict the amount of the shift of the vibrational frequency of the OH stretch mode of the water molecule. For that purpose, we employ the machine learning technique and use neural networks. Neural networks consist of layers, and layers contain nodes. The first layer is called the input layer, the last layer is called the output layer, and the layers in between the two layers are called hidden layers. Each node implements mathematical calculation using the numbers passed to this node from the nodes in the previous layer. If we give some information to the input layer after a series of stepwise calculations at each layer, the neural network gives the final answer at the output layer. We train this neural network to produce the amount of vibrational frequency shifts of the water molecule when the structural information of the water configuration is given to the nodes in the input layer. After the training procedure, we found that the trained neural networks can predict the amount of the frequency shift of the OH stretch vibrations of the water molecules. We also trained the neural network to predict the transition dipole moments of the OH stretch vibrations of the water molecule, and found that the trained neural network can predict the transition dipole moments. We check that the vibrational frequencies predicted by the trained neural network are in good agreement with the results of quantum chemistry calculations. The present study has been published this year in the Journal of Chemical Theory and Computation. When you are more interested in details of this study, you can consult this paper. Thank you for watching this video. Bye.